We're going to start off today with an introduction to building with Kubernetes. So in this module, we'll introduce you to Uptime Flowers, which will be an online flower shop that wants to migrate their monolith architecture to microservices to improve scalability, reliability, and fault tolerance. Uptime Flowers is our example company that's kind of an amalgamation of various experiences with many different types of companies. So you'll see some common themes and strategies that they'll want to adopt. You'll find out how containers in Kubernetes can help provide an effective path for migration and explore the basic components of Google Kubernetes Engine. You'll also learn how to describe and compare monoliths and microservices, as well as containers and virtual machines. You'll be able to explain the basics of Kubernetes architecture and identify uses and benefits of key components of Google Kubernetes Engine. So let's get started. This is Uptime Flowers' current architecture. Its auto-scaling managed instance groups all receive user traffic through cloud load balancing, which would be an HTTPS global load balancer. And they scale up or down depending on that traffic. They perform all the business logic with multiple internal software components that we'll describe in more detail later. All relevant state and data are stored in a Cloud SQL Postgres database. And there's a read replica to offload read requests that can be promoted to a primary during failures or maintenance of the current primary. Uptime Flowers has found this architecture has become difficult to scale in a cost-effective way, as some of their software components require more resources than others, but they can only auto-scale the entire monolith altogether at the same time. Uptime Flowers, like many businesses that I encounter, are looking to modernize their architecture and improve its scalability. They, like many companies, think that microservices and containers may help. Let's consider that and how these approaches, these various styles of architecture, have kind of come about over the last 25 years of software development. Historically, organizations owned or leased their own infrastructure and data centers and built and deployed their software onto bare metal servers. This meant that rarely was anything utilized at 100% efficiency. There was usually lots of idle resource time. And the first big efficiency improvement that really started to be adopted here was for data centers themselves to be shared or co-located, also called colos. So this was kind of an improvement in the efficient usage of the physical space needed to host these machines. And then as virtualization started to become more popular, VMs or virtual machines enabled more efficient use of that infrastructure, of the actual machines. Also allowed for things like multi-tenancy and more third-party infrastructure, as well as better workload isolation and dependency management, which is kind of related. So then the cloud was born and infrastructure as a service started to become more common. And then next, the arrival of and rapid adoption of the container allowed for even more efficient use of infrastructure and facilitated deploying and scaling smaller independent microservices, which would then give rise to platforms as a service. A little note on the history of containers here. There were, of course, early iterations of containers, such as FreeBSD and Solaris, FreeBSD zones and Solaris jails. And then the Linux Container Project, LXC, was kind of an early iteration of containers on the Linux kernel, kind of built in, the components of containers being built into the Linux kernel. But they were kind of difficult to use, and containers really started to take off in around 2014 with the advent of Docker, which a lot of you have probably heard about. Docker came along and made using containers a lot easier. It wasn't the first iteration of containers, but it was the one that made them easier to a point where they became a lot easier for a lot of companies to adopt. So this trend of further offloading infrastructure management to the cloud provider has continued and led to even more adoption of managed services from cloud providers, as well as the concept of serverless, where a company wants to basically might as well pretend that the servers don't even exist. You really want to focus on the things that are at a higher level rather than focusing on the servers themselves. So that's kind of the goal both of managed services and of serverless, is to kind of abstract away those lower levels and let businesses focus on what really matters to them. However, with any of these approaches, there are, of course, trade-offs to consider. As organizations offload more of the infrastructure management to the cloud provider via platforms as a service, or managed services, or serverless, they give up some of their infrastructure control and flexibility. For example, the choice of infrastructure options, actual hardware options. Or I guess in the case of the cloud, often with virtual machine instance types, it's often kind of the shapes, as we call them. Uptime Flowers, like many companies, is looking to strike this balance between having some amount of control and flexibility over their infrastructure choices, while also offloading as much as they can, as much as is reasonable, so that they can focus on the parts of their business that are really unique to their business and that they want to spend most of their time on. So, Uptime Flowers realizes that microservice architectures are the current trend, but as any company should, they want to ensure that there's a good reason for them to select microservices as their approach. And one reason for microservices that appealed to them and appeals to many businesses is that it enables teams to work more independently and deliver through to production at their own cadence. This supports scaling the organization. Adding more teams should, in theory, allow them to increase speed. And another reason is the benefit of being able to scale their microservices independently based on their requirements. That in particular really appeals to Uptime Flowers because in their case, they have a website, of course, where they sell flowers. And part of that is a products service, what we'll call a product service, which is used for browsing their product selection. And that typically handles a lot more traffic than their orders service, which is then used for purchases. Makes a lot of sense for customers on an online business to spend more time browsing than they do actually placing orders. So architecturally, a monolith or microservices should be modular components with clearly defined boundaries. With a monolith, the deployment is the group of all components, whereas with microservices, the individual components are independently deployable, upgradable, and scalable. Uptime Flowers realized that Google Kubernetes engine could give them a path to deploy their existing monolith architecture, and then slowly over time start moving it toward a microservices architecture. This is a really common pattern that I see. A lot of businesses have these monolithic applications, which made a lot of sense traditionally, but now they're starting to look at application modernization, they're starting to look at microservices, and that change doesn't happen overnight. You have to think about the time that that's going to take you and the steps you're going to take along the way. And we'll go over a strategy a little bit later for transitioning your monolith into microservices. So to achieve independence of their services, each stateful service is also going to have its own database, is kind of what Uptime Flowers is thinking here. And ideally, many of the services in a microservice should be stateless. By separating out each service and making sure that each service has its own database, that allows each team to choose the best database solution for that specific service. And also decreases the coupling of services through a shared database. As you start to distribute your application out more, you have to think about where is that data going to be. My application is distributed across a variety of machines, a cluster of machines. You have to think of really about where that data is going to be as well. So there are a number of advantages to microservice architectures. And the pros include microservice architectures being easier to develop and maintain. For a lot of developer teams, having a smaller chunk of the overall application that they own and that they have to develop and maintain means that they can do so a bit more easily. There's also reduced risk when deploying new versions, which we're hoping we'll be able to do more frequently, which will be one of our later points here. So when you're deploying all of these new versions, if you are trying to deploy everything onto the same virtual machine, there's a higher risk that a breaking change in one component could have stronger effects on other pieces of your overall application. If you're splitting them out into microservices, into a microservice architecture, an issue in one piece of the microservice architecture should, in theory, be able to be more easily detected and less likely to cause problems throughout the entire application. So reduced risk in deploying new versions. Services also can scale independently to optimize use of infrastructure. We talked about that. It's faster to innovate and add new features. Like we said, if a team has a smaller component of the application that they have to worry about as their own, then they should, in theory, be able to innovate more quickly on it and release new features more quickly. Also means that you would be able to use different languages and frameworks for different services. Having them decoupled like this also means some benefits for your talent pool. If you choose to have different languages or frameworks for different services, you can choose depending on the talent that you have available to you or depending on what is most relevant to the application. And so that can also have benefits in your hiring pool as you start looking outside of the company, looking to hire. You can look at a wider variety of skill sets. And of course, you can choose the runtime that's appropriate for each service, which is nice. However, with any architectural choice, there are cons as well. So these include increased complexity when communicating between services. If you're taking your single monolith and splitting it out into smaller services that then have to communicate with each other, creating this kind of distributed system of services, that means increased complexity. And with that more distributed architecture means that you'll have increased latency across service boundaries as those different microservices have to communicate with each other and may be more distributed across a larger cluster of actual machines. There are also then, of course, concerns about securing inter-service traffic. If you have all the services communicating with each other across the network, then you have to worry about securing that traffic. An increased number of deployments also means that there's more things to worry about as each piece of the microservice hopefully iterates faster and deploys quicker. There's more that you have to worry about, such as worrying about ensuring that you don't break clients as versions of independent pieces of the microservice change. And also maintaining backward compatibility with clients as the microservice capabilities and interfaces evolve, especially within the microservice, making sure that each component as it updates is still working with all of the other components of the microservice is, of course, very important. Uptime Flowers, like a lot of businesses, is still interested in microservice architectures. Another benefit that I didn't really mention is that, of course, microservices are a popular trend. A lot of businesses are adopting them. And so as you think about moving forward, a lot more of the talent pool is going to have expertise with these more modern application architectures. So moving your monolith now should provide, in theory, benefits later on down the line as technology and architectures continue to evolve. Of course, this train isn't stopping. There's going to be changes coming down the line as we go beyond microservices. So migrating now means that they'll be more ready for the changes that are coming in the future. So now that Uptime Flowers has made the decision to switch from monolithic architecture to microservices, the next question for them is whether to deploy their microservices as virtual machines or as containers. So let's look more closely at the differences between these two deployment methods. So running a monolith consisting of multiple services within a VM creates a problem. Services that share dependencies are not isolated from each other if you're running them all within the same virtual machine. The service requirements or the resource requirements of one service can starve other services of the resources that they need. Also, a dependency upgrade for one service might cause another one to stop working because they're sharing dependencies all on the same virtual machine. And additionally, features or failures in one service can cause the entire virtual machine to fail, which would, of course, bring down all of the services that are running on that virtual machine together. And of course, there's no way to independently scale the component services of the monolith, which is one of the big reasons that Uptime Flowers started looking at microservices to begin with. So one way to solve this problem is by moving to microservices on separate virtual machines. So in this case, each service maintains its own dependencies and the kernel is isolated so that this just one service won't take all of the resources for another service. And a failure won't impact all of the services on the machine either, as long as just one component is failing. As long as the components are isolated on virtual machines, one component failing on one virtual machine shouldn't affect the other virtual machines. Yeah, it's a good way to describe it. However, a problem with this approach is that 2 complete copies of the kernel have to be running and consuming resources. You have to do the whole hardware virtualization component of virtual machines, and this requires a lot of overhead in terms of disk space, memory, CPU, all of your resources on your actual machine. So if we start thinking about scaling this to hundreds of or thousands of microservices, you start to see its limitations. So for large microservice-oriented systems, dedicated virtual machines are redundant and wasteful. Virtual machines are also relatively slow to start up because the entire operating system has to boot, as well as doing all of the hardware virtualization of a virtual machine. So a more efficient way to resolve the dependency problem for microservices is to implement abstraction at the level of the application and its dependencies. Then you don't have to virtualize the entire machine or even the entire operating system, but just the user space. The user space is all of the code that resides above the kernel, and it includes applications and their dependencies. So that's what it means to create containers. Containers are isolated user spaces for running service code. They are the evolution of operating system processes, really. So containers are lightweight because they don't carry the full operating system. They depend on the kernel underneath. They can be scheduled or packed tightly onto the underlying system, which is very efficient in terms of using resources, and they can be created and shut down very quickly because they don't have to start up the whole operating system every time. They don't have to do all of the hardware virtualization and everything either, so they're a much lighter weight form of isolation. Developers often appreciate this level of abstraction because they don't want to worry about the rest of the system. Containerization is kind of the next step in allowing them to manage the evolution of, the next step in the evolution of managing code, I guess is a good way to say it. This is the approach that Uptime Flowers has chosen, and so this should help them with their scaling efficiency concerns that they were talking about earlier. So you now understand containers as delivery vehicles for services. They're lightweight, standalone, resource-efficient, portable, executable packages. You develop service code in the usual way, on desktops, laptops, and servers. The container allows you to execute your final code on virtual machines without worrying, or bare metal, or wherever you want to, without worrying about software dependencies like application runtimes, system tools, system libraries, and settings. You package your code with all of the dependencies that it needs, and the engine that executes your container is responsible for making sure that those are available at runtime of your application. So containers allow developers to safely make assumptions about the underlying hardware and software. With a Linux kernel underneath, you no longer have code that works on your laptop but doesn't work in production. This is a very common benefit that I hear about containers is they've been kind of billed as solving the it works on my machine problem. Because ideally with containers, you have everything that the application needs all packaged up with it in the container. So it should work the same anywhere you run it. And if you make incremental changes to a container based on a production image, you can then deploy it very quickly with a single file copy, just the container image, which we'll talk about here in a minute. So that should speed up development. Finally, containers make it easier to build applications that use the microservices design pattern. That is, loosely coupled, fine-grained components. This modular design pattern allows the operating system to scale and upgrade components of an application without affecting the application as a whole. A service and its dependencies are called an image in containers, like I just mentioned, and a container is simply a running instance of a container image. So by building software into container images, developers can easily package and ship an application without having to worry about the system that application will actually be running on. You need software to build container images and to run them. Docker is one tool that does both. Like I mentioned earlier, Docker came along in about 2014 and really made containers a lot easier to use. So Docker is an open source technology that allows you to create and run applications in containers, but it doesn't offer a way to orchestrate those applications at scale as Kubernetes does. There's Docker Swarm, but Kubernetes is by far the most common tool used to manage containers at scale. It has definitely become the standard. So in this course, we will use Google Cloud's Cloud Build to create Docker formatted container images that we'll then use in Kubernetes. Hint, hint. Spoilers for later. So containers are not an intrinsic primitive feature of Linux. Instead, their power to isolate workloads is derived from the composition of several technologies within the Linux kernel. One foundation is the Linux process. Each Linux process has its own virtual memory space, separate from all other processes on the machine, and Linux processes are rapidly created and destroyed. Containers use Linux namespaces to control what an application can see: process ID numbers, directory trees, IP addresses, and more. And by the way, Linux namespaces are not the same thing as Kubernetes namespaces, which we'll teach you about a little bit later in this course. So containers use Linux C groups to control what an application can use. So it uses namespaces to control what an application can see, and then C groups to control what an application can use. That's in terms of maximum consumption of CPU time, memory, I/O bandwidth, and other resources. And containers use union file systems to efficiently encapsulate applications and their dependencies into a set of clean, minimal layers. So let's talk a little bit more about container layers. A container image is structured in layers. The tool you use to build the image reads instructions from a file called the container manifest. In the case of Docker formatted container images, this is what we call a Docker file. So if you've encountered one of those before, each instruction in the Docker file specifies a layer inside the container image. Each layer is read-only. When a container runs from this image, it will also have a writable, ephemeral topmost layer. So let's take a look at a simple Docker file with just a few commands. And each one of these commands creates a layer. So the from command, the from statement here at the top of our Docker file, starts out by creating a base layer, which will be pulled from a public repository. This one happens to be the Ubuntu Linux runtime environment of a specific version. The copy command adds a new layer containing some files copied in from your build tool's current directory. This is one way that we get important application files or other files into our container. And then the run command builds your application using the make command and puts the results of the build into a third layer of our container. Well, container image. And finally, the last layer specifies what command to run within the container when it's launched. So each layer is only a set of differences from the layer before it. When you write a Docker file, you should organize from the layers that are least likely to change, like our base image, through to the layers that are most likely to change. Like at some point, you may be more likely to change the command that happens on startup when the container starts. When you launch a new container from an image, the container runtime adds a new writable layer on top of the underlying layers, and that layer is often called the container layer. All changes made to the running container, such as writing new files, modifying existing files, and deleting files, are written to this thin, writable container layer, and they're ephemeral. This is very important. So when the container is deleted, the contents of this writable layer are lost forever. The underlying container image remains unchanged. The fact about containers is that they have this implementation where when you are running the container, any changes that you make to the running container are not saved in the container image itself. So whenever you want to store any data permanently, you have to do so in some place other than in the running container, which kind of helps with documentation in a way. It's kind of nice in certain circumstances. Because each container has its own writable container layer, all state changes are stored in this top layer. Multiple containers can share access to the same underlying image and yet have their own data state. So this diagram shows multiple containers sharing the same Ubuntu image. Because each layer is only a set of differences from the layer before it, you get smaller images. So for example, your base application image may be 200 megabytes, but the difference between that and the next point release might only be 200 kilobytes. So when you build a container, instead of copying the whole image, it creates a layer with just the difference. When you run the container runtime pulls down the layers that it needs. And when you update, you only need to copy the difference. That's a lot faster than having to run a new virtual machine every time. So it's very common to use publicly available open source container images as the base for your own images, or for unmodified use. For example, you've already seen the Ubuntu container image, which provides an Ubuntu Linux environment inside of a container. Alpine is another popular choice for a Linux environment in a container, which is especially popular because it's very, very small in terms of its resource footprint. The Nginx web server is also a very frequently used container image. Google maintains its own container registry, gcr.io or Google Container Registry.io. This registry contains many public open source images, and Google Cloud customers can also use it to store their own private images in a way that integrates with Cloud Identity and Access Management, or IAM. So Google Container Registry is integrated with Cloud IAM. So for example, you can use it to store images that aren't public. Instead, they are private to your project. You can also find and use container images from other public or private repositories, such as Docker Hub Registry, GitLab, and all sorts of others. The open source Docker command line tool is a popular way to build your own container images, and it's widely known and widely available. One downside of building containers with the Docker command is that you must trust the computer that you do your builds on. Google provides a managed service for building containers that's integrated with Cloud IAM, and that service is called Cloud Build, and that's what we'll be using in this course. So Cloud Build can retrieve the source code for your builds from a variety of storage locations, from cloud source repositories, cloud storage, which is Google Cloud's object storage service, or Git-compatible repositories like GitHub and Bitbucket. To generate a build with Cloud Build, you need to define a series of steps. For example, you can configure build steps to fetch dependencies, compile source code, run unit or integration tests, or use tools such as Docker, Gradle, or Maven. Each build step in Cloud Build runs inside of a Docker container. And then Cloud Build can deliver your newly built images to various execution environments, not only Google Kubernetes Engine, but also App Engine, Cloud Run, Compute Engine, and Cloud Functions. So coming back to Uptime Flowers. Uptime Flowers has decided to move to a microservice architecture with microservices deployed as containers. So how will they manage that increased complexity? Kubernetes, of course, is the most popular choice, I would say. So what is Kubernetes? It's a container orchestrator, a container-centric management environment. Its origins come from something called Google Borg. If you've ever heard of the Borg papers, you can Google that, or Google Borg. Google Borg. So Google Borg was Google's internal system for running containers. Google has been running containers for over a decade. They started using containers before the advent of Docker and the current popularity of containers. I know, before it was cool. So, so since they were using containers so early on, they had to have some way to manage containers at scale, and that was Google's Borg system. And at one point, a bunch of engineers, well, three Google engineers decided, hey, this Borg system for running containers makes a lot of sense, and I bet a lot of other companies would like to use it. And they kind of generalized that out into Kubernetes. So Kubernetes has its origins in Google's own container orchestration system called Borg. Now, of course, it's a project of the vendor-neutral Cloud Native Computing Foundation, of which I am an ambassador. Just mention. So Kubernetes also facilitates the features of infrastructure as a service, such as allowing a wide range of user preferences and configuration flexibility. I actually know someone who once ran a Kubernetes cluster on a bunch of Android watches. It's a pretty flexible open source project. So Kubernetes supports declarative configurations. That's one of its major upsides, major benefits that people really like Kubernetes for. And this means when you administer your infrastructure declaratively, that means that you are describing the desired state that you want to achieve instead of issuing a series of commands to achieve that desired state. So Kubernetes' job is to make the deployed system conform to your desired state and to keep it there in spite of any potential failures that might happen. Declarative configuration generally is meant to save you work because the system's desired state is always documented. It also reduces the risk of error and improves idempotency of operations since it's already documented there. Kubernetes also allows for imperative configuration, it should be mentioned, in which you issue commands to change the system's state more dynamically. But administering Kubernetes at scale imperatively would be a big missed opportunity. One of the primary strengths of Kubernetes is its ability to automatically keep a system in a state that you declare. So experienced Kubernetes administrators will generally use imperative configuration only for quick temporary fixes and as a tool for building declarative configurations. By the way, if you're interested in being a Kubernetes administrator, you think that might be your task, there is a certification for that the Linux Foundation offers. Just so you know. Now that you know what Kubernetes is, let's talk about some of its features. So Kubernetes supports different workload types. It supports stateless applications such as Nginx or Apache web servers, and stateful applications where user and session data can be stored persistently. It also supports batch jobs and daemon tasks. So you can specify resource request levels and resource limits for your workloads, and Kubernetes will obey them. These resource controls let Kubernetes improve overall workload efficiency within a cluster. Developers extend Kubernetes through a rich ecosystem of plugins and add-ons. So for example, there's a lot of creativity currently going on with Kubernetes custom resource definitions, or CRDs, which bring the Kubernetes declarative management model to an amazing variety of other things that need to be managed. Custom resource definitions are really cool, and there are a lot of talks about them if you want to check it out. And because it's open source, Kubernetes also supports workload portability across on-prem or multiple cloud service providers, such as Google Cloud and others. This allows Kubernetes to be deployed anywhere. So you can move Kubernetes workloads freely without vendor lock-in. It's one of the ideals that a lot of businesses seek out Kubernetes for. Like I mentioned, Kubernetes can be run just about anywhere, even on a bunch of Android watches. So Kubernetes works with clusters of computers. They can be physical machines or virtual machines. They always are virtual machines in Google Kubernetes engine, specifically in that case. So one or more computer is called the control plane, and the others are called simply nodes. The main job of the nodes is to run pods, which are essentially your workloads. You'll hear me using pods and workloads pretty interchangeably. Technically, pods are a Kubernetes API object, which you should definitely learn more about. They are essentially how Kubernetes thinks about containers. I think I'll talk about that a little bit more later, but I'll be using pods and workloads pretty interchangeably here for a few slides at least. The job of the control plane is to coordinate the entire cluster, but we'll discuss the components first. So several critical Kubernetes components run in the control plane. The single component that you interact with directly is the Kube API server. This component's job is to accept commands that view or change the state of the cluster, including launching pods or workloads. So you'll be using the kubectl command frequently if you're acting as a Kubernetes administrator and interacting with the Kube API server. The kubectl command's job is to connect the Kube API server to the Kube API server and communicate with it using the Kubernetes API. Kube API server also authenticates incoming requests, determines whether they're authorized and valid, and manages admission control. But it's not just kubectl that talks with Kube API server. In fact, any query or change to the cluster's state must be addressed to the Kube API server. etcd, or as some people call it, etcd, is the cluster's database. Its job is to reliably store the state of the cluster. This includes all the cluster configuration data and more dynamic information such as what nodes are part of the cluster, what pods should be running, and where they should be running. You never interact directly with etcd. Instead, the Kube API server interacts with etcd, which I call it the database, but it's more commonly referred to as a key value store. Same thing, really, in some ways, right? Anyway, so Kube API server interacts with etcd on behalf of the rest of the system. Kube Scheduler is responsible for scheduling pods or workloads onto actual nodes. To do that, it evaluates the requirements of each individual pod and selects which node is most suitable. But it doesn't do the work of actually launching pods on nodes. Instead, whenever it discovers a pod object that doesn't yet have an assignment to a node, it chooses a node and simply writes the name of that node onto the pod object. Another component of the system is responsible for then launching the pods, which we'll see in a minute. So how does Kube Scheduler decide where to run a pod? The Kube Scheduler knows the state of all of the nodes, and it will obey constraints that you define on where a pod may run, which may be based on hardware, software, and policy. For example, you might specify that a certain pod is only allowed to run on nodes with a certain amount of memory. You can also define affinity specifications, which cause groups of pods to prefer running on the same node altogether because they're friends. Or anti-affinity specifications, which specify that pods do not run on the same node because they are not friends. Kube Controller Manager has a broader job. It continuously monitors the state of a cluster through Kube API server. Whenever the current state of the cluster doesn't match the desired state, which we talked about earlier, remember when we were talking about declarative. So whenever the current state doesn't match the desired or declared state, Kube Controller Manager will attempt to make changes to achieve the desired state. It's called the Controller Manager because many Kubernetes objects are maintained by loops of code called controllers. These loops of code handle the process of remediation. Controllers will likely be very useful to you. To be specific, you'll use certain kinds of Kubernetes controllers to manage workloads. For example, if we wanted to keep 3 Nginx pods always running, we can gather them into a controller object called a deployment. that both keeps them running and lets us scale them and bring them together underneath a front end. Other kinds of controllers have system-level responsibilities. For example, node controller's job is to monitor and respond when a node is offline. Kube Cloud Manager manages controllers that interact with underlying cloud providers. For example, if you manually launched a Kubernetes cluster on Google Compute Engine, then Kube Cloud Manager would be responsible for bringing in any Google Cloud features like load balancers and storage volumes whenever you needed them. This has been a big improvement from when I first started using Kubernetes. The cloud managers are a really, really nice feature. Just gonna mention. And each node runs a small family of control plane components as well. The main one that each node runs is called the kubelet. So you can think of a kubelet as Kubernetes agent on each node. When the Kube API server wants to start a pod on a node, it connects to that node's kubelet. This is part we mentioned earlier, if you remember. So the kubelet uses the container runtime that's actually on the node to start the actual container, which from Kubernetes perspective is basically a pod. The pod is running your containers, which kubelet has started using the container runtime on the node. And then the kubelet also monitors the lifecycle of that pod, including readiness and liveness probes, and reports back to Kube API server. Each node also runs the container runtime, like we mentioned. This is software that knows how to launch the container from a container image. The world of Kubernetes offers several choices of container runtimes, but the Linux distribution that GKE uses for its nodes launches containers using containerd, which is the runtime component of Docker. So kubeproxy's job is to maintain the network connectivity among pods in a cluster. In open source Kubernetes, it does so using the firewalling capabilities of IP tables, which are built into the Linux kernel. So later we'll learn how Google Kubernetes Engine handles pod networking. So we've established that Uptime Flowers wants to use Kubernetes to manage their containerized microservice architecture. But they would rather not have to manage any more infrastructure than they really have to. So in Google Cloud, what we have to help is Google Kubernetes Engine. So Google Kubernetes Engine, or GKE, is a fully managed Kubernetes service, which means you don't have to provision the underlying resources. However, it still gives you the control and flexibility and choice of infrastructure. Depending on what mode you choose, you have more flexibility and more choice, which we'll talk about more later as we dive more into GKE. So this is the solution that Uptime Flowers is going to utilize, at least in this course. So GKE uses a container-optimized operating system to run your workloads. These operating systems are maintained by Google and are optimized to scale quickly with a minimal resource footprint. When you use GKE, you start by directing the service to instantiate a Kubernetes system for you. This system is called a cluster. Kubernetes clusters. So GKE's auto upgrade feature can then be enabled to ensure that your clusters are always automatically upgraded with the latest stable version of Kubernetes. The virtual machines that host your containers in GKE are called nodes. If you enable GKE's auto repair feature, the service will repair unhealthy nodes for you. It'll make periodic health checks on each node of the cluster, and if a node is determined to be unhealthy or require repair, then GKE will drain the nodes. In other words, it'll force the workloads that are running on that nodes to go run somewhere else. And just as Kubernetes supports scaling workloads, GKE supports scaling the cluster itself. So GKE integrates with Google's Cloud Build and Container Registry for managing your container images, which allows you to automate deployment using private container images that you've stored in Container Registry. So GKE also integrates with Google's Identity and Access Management, or IAM, which we've been talking about earlier, which allows you to control access through the use of accounts and role permissions. And Google Cloud's Operations Suite Google Cloud's Operations Suite is a system for monitoring and managing services, containers, applications, and infrastructure. GKE integrates with cloud monitoring to help you better understand your application's performance. GKE has integrated with Google Virtual Private Clouds and makes use of Google Cloud's networking features. And finally, the Cloud Console provides insights into GKE clusters and their resources and allows you to view, inspect, and delete resources in those clusters. So you might be aware that open source Kubernetes contains a dashboard, but it takes a lot of work to set that up securely, particularly. So having the Cloud Console have a dashboard for your GKE clusters is really nice and means that you don't have to manage it as much, and it's generally much more powerful than the Kubernetes open source dashboard. So there's an open source command called kubeadm that can automate much of the initial setup of a cluster, but if a node fails or needs maintenance, then a human administrator would have to step in and respond manually. And that's the sort of scenario where a managed service can really come in handy. GKE manages all the control plane components for you. It still exposes an IP address to which we send all of our Kubernetes API requests, but GKE takes responsibility for provisioning and managing all of the control plane infrastructure behind it. So it also abstracts away having a separate control plane, and the responsibilities of the control plane are absorbed by Google Cloud, and you're not separately billed for your control plane. So Uptime Flowers is now ready to start moving their monolith into GKE and then begin the process of converting it into microservices. So how would that process look? In Kubernetes, each object is of a certain type or kind, as Kubernetes calls them. Pods are the basic building block of the standard Kubernetes model, and they're the smallest deployable Kubernetes workload. Perhaps you suspected the smallest Kubernetes object is the container, but not so. Every running container in a Kubernetes system runs inside of a pod, which is why I also referred to them as workloads earlier. That's where your containers are. So a pod embodies the environment where the containers live, and that environment can accommodate one or more containers. This can provide a path of bringing a monolith into Kubernetes as a single container or a single pod, and iteratively migrating it to a group of microservices spread across multiple pods. So if there's more than one container in a pod, they are tightly coupled and share resources including network and storage. Kubernetes assigns each pod a unique IP address. So every container within a pod shares the network namespace, including IP addresses and network ports. Containers within the same pod can communicate through localhost, and a pod can also specify a set of storage volumes to be shared among its containers within the same pod. So the most common use case for having multiple containers in a pod is something like a sidecar, something that has to work really, really closely with the other container. But by far the majority of pods are a single container in terms of the microservice architecture. So Uptime Flowers will use a popular pattern for migrating their monolith to microservices, which is called the Strangler pattern. This pattern attempts to convert portions of a monolith to a microservice in isolation, while leaving the rest of the components as is, as part of a shrinking monolith. So this pattern is named after the Strangler fig vine. I thought maybe it was somebody's name or something, but it's actually named after a vine that slowly grows by wrapping around and killing off the underlying tree, much like microservices grow, eventually killing off the monolith. So you can utilize that same pattern with Kubernetes to convert from a monolith in a single container of a single pod to a group of microservices, each in their own container and their own pod. So migrating a monolith to a single container in a single pod of Kubernetes is the simplest possible first step and ensures that the latency and chance of error between the software components stays the same as it was previously when the monolith was deployed directly to a virtual machine. This is how Uptime Flowers begins their journey and how a lot of companies that I've seen look to begin their journeys. So this is just a first step. Ultimately, this is still a monolith running in Kubernetes and still has the same problems that a monolith has. Shared dependencies, lack of resource or failure isolation, inability to deploy, upgrade, or scale components. independently, so still all of the problems of a monolith. But using the strangler pattern, the associated teams can work on converting their software components into distinct containers by replacing the communication and data exchange with the other software components to utilize a network protocol rather than a static or dynamic linking of some sort, or other in-process ways of passing or exchanging data. Eventually, all the components are going to be converted to separate containers communicating via network protocols. However, this can still be considered to behave somewhat like a monolith. The components can be given isolated resources or dependencies, and still fail in an isolated and independent way, which is like microservices, but they can't be deployed, upgraded, or scaled independently as long as they're in the same pod. So in that sense, they're still like a monolith. However, the evolution will continue as we start breaking off components of this monolith, which we've now split into separate containers, and now we're going to start running those containers in separate pods. So as the next step in evolution, each software component's intercommunication to other components can be made more robust to support the varying latency and error rates that can arise from being run and scaled independently in this new distributed system that we're building. They can even potentially be on different host nodes. So we want to make sure that we are ready for that change in the networking between the components. Once this update is complete, each component container can be split apart one by one into a fully independent microservice pod, which can then be scaled and deployed independently. And when that process is completed, Uptime Flowers will have completed the migration from monolith to microservices. The beauty of Kubernetes is that each step can be done as quickly or slowly as desired, and it's easily reversible if any problems are encountered. Now we're going to test your knowledge of what you've learned so far in Module 1 with a little quiz. So our first question here is, which of the following is a benefit of microservice architectures relative to monolithic architectures? A, microservices never fail. B, microservices have better performance. C, microservices can scale independently. D, microservices work better with databases. So there should be a form next to me on the screen that you can put your answers into, or you could just write them down for your own benefit if you'd like. Okay, and for our first question, the correct answer is microservices can scale independently. That's something that we talked about quite a bit in this module, and one of the main reasons that our example company of Uptime Flowers wanted to move to microservices so that they could scale the pieces of their monolith as individual services more independently. For question 2, which of the following are benefits of deploying microservices via containers? Containers are more secure than virtual machines. Containers are smaller. Containers run over a common kernel, or containers start up and scale faster. And you may select more than one of these. So again, containers are more secure than virtual machines. Container images are smaller. Containers run over a common kernel, or containers start up and scale faster. Okay, I'll give you just a couple more seconds. All right, and the correct answers for this one were container images are smaller, containers run over a common kernel, and containers start up and scale faster. We talked about all of these during our module as we explained what containers are and why you might want to use them for microservices. Which of the following are components of the Kubernetes control plane? The Kube API server, the Kube scheduler, the pod, or the Kube proxy? Okay, and the correct answers for this one are all of the ones with Kube at the start of them. We went over the control plane components earlier, and Kube API server, Kube scheduler, and Kube proxy are all important parts of the control plane. What were the reasons Uptime Flowers chose GKE? They want to migrate a monolith to microservices. They wanted to retain some choice of infrastructure, they wanted to deploy their software as containers, or they needed the simplest possible deployment method. And you may select more than one of these. I'll give you a few seconds to answer. So the correct answers are the first three. They wanted to migrate a monolith to microservices. We talked about that in the Strangler pattern that Uptime Flowers was considering using for transitioning their monolith and modernizing it into microservices. They wanted to retain some choice of infrastructure. We mentioned this earlier about the trade-offs that you make between handing off control of your choices in terms of using a managed service versus choosing things yourself. And then they wanted to deploy their software as containers, and we talked through that decision. So that's it for our quiz for today. I hope you enjoyed the session.